Hey everyone, it's Nolan, and in this video I'll be doing a walkthrough of a typical flow or burn with the Eureka 1 system. So that's everything including the preparation for a flow all the way to the end of the flow or burn itself. And I'll especially be looking at it through the lens of the data, since after all the reason we do most of these flows is to collect more data and just gain a better understanding of our system so that we're better able to predict how it's going to behave once we eventually fly the system. And I think understanding a flow through the lens of the data is kind of critical to understanding the system as a whole and how it works and kind of the underlying physics of what's going on when we do these flows. And the more familiar you become with what a nominal perfect flow looks like, the better you'll get at spotting anomalies or inconsistencies in the data when things don't go the way they're supposed to, because a lot of times it's not immediately obvious just by looking at the system during the flow itself. And so spotting these anomalies is a super useful skill, especially as we do more and more of these flows. We want to be able to catch even the smallest things that don't go the way they're supposed to. Also, knowing what you're looking at when you're looking at the data is pretty important and pretty useful for just learning new things about the system. I think a lot of the revelations we've made about the system kind of happen after the fact when we're staring at the data and we ask ourselves the right questions about a certain feature in the data, and that's a good way to gain new information after the fact. I'm sure there's a lot of things we still can learn from the data that we haven't, just because we haven't looked deeply enough into it. So without further ado, let's get into it. Okay, so all the flows we do have a corresponding test ticket in the SebJira, and they're numbered in chronological order, which you can see here. So the most recent tests we did were these two hot fires in June of 2022. Those were hot fire 6, burn 1 and 2, which you see here. And so the test we'll be using as an example in this video is test 100, which I have pulled up here. And this was our first full duration hot fire with the Eureka 1 system. And you can see the ticket contains a lot of information about the test itself, as well as 2 links to chronograph data. And so the first one is labeled full, and this contains the full procedures of the flow. So everything, like I said before, including the preparation and the flow itself. And so the other link, which is included in this first frame of data, is just the flow itself. And so that's just the 15 to 20 second frame of the flow itself, which we'll get to. But for now, we'll be looking at this sort of macro view, and this is around an hour to 40 minutes, something around there, of the full procedures. And so I'll go into more detail of each step of the procedures, but just as a quick overview, what you see at the beginning here is filling the dome ports. The next step would be pressure and fill, which you see here. After that, we have propellant fill, where we fill the propellants, followed by propellant pressurization, which is this spike in pressure in the propellant tanks right here. And then after that, we're ready to flow, and the flow is this little spike in the injector pressure that you see right here. Another way to look at that is with the thrust. So the flow itself is just a small piece of this entire procedures. And so we'll go into more detail of each of these steps. So the first step of the procedures is to pressurize the dome ports, or fill the domes, which is what you see right here under the dome pressures. And so real quick, going back to our diagram of the system, you'll see right here that the dome volumes, or the dome ports, are these small volumes on the pressure regulators for both propellants, whose pressure determines what pressure the regulators will regulate down to once the pressurant ball valve is opened. And so what we do, if you remember from the plumbing overview video, is we connect to the dome port via this QD with an external hose. We open this ball valve, and then we pressurize this volume for both regulators, and we monitor the pressures with this PT right here, directly downstream of the regulator. And so these 2 PTs, going back to the data, record the pressures that you see right here under dome pressure. That's fuel dome PT and LOX dome PT. So these are reading the pressures of the dome port. And so you see first here what we do is we fill, and I'll zoom in right here a little bit. The first thing we do is we fill the fuel dome port. So it goes from basically ambient pressure all the way up to the pressure we want it to be, around 640 in this case. And then we also fill the LOX dome. So here it starts off pressurized a little bit, and you can see that we open the ball valve to vent it, get it back to 0, and then we pressurize it to the pressure that we want it to be at, which is around 440 psi in this case. And then the dome ports will stay at this pressure throughout the duration of the procedures until the flow. Okay, back to our full view, you'll see that the next step in the procedures is pressurant fill, and that's this increase in pressure under pressurant. So let's look at the diagram real quick. So pressurant fill is the process where we connect an external source of gaseous nitrogen via this QD and fill the pressurant tank, the N2 tank, along with a little bit of volume of hardline downstream of the tank all the way to the RBV, or the remote ball valve right here. And so as we fill, we're monitoring the pressure of the pressurant tank with this PT that branches off the bottom of the tank, and that's the high pressure or pressurant PT, whose values you can see we were just looking at in this plot. And so you can see at around 1050 here, we start pressurizing the pressurant tank. The pressure increases gradually all the way up to 2000, and then it keeps going all the way to the pressure needed to sustain the full burn, which is somewhere between 3.5 and 4.5 thousand psi. And so you'll notice that there's a step here where we stop pressurizing, and this is because we're actually using 2 different bottles of gaseous nitrogen to pressurize this volume. So the first bottle we use is a 2000 psi bottle, which explains why it stops at around 2000, and then we switch it out for a 6000 psi bottle to make it all the way to the full pressure. And the reason we do that is because the 2000 psi bottles are much cheaper, so it's better to use those lower pressure bottles to get up to as high as we can, and then switch it out for the more expensive higher pressure bottles. And so you can see this is around a 10-minute process where we are just increasing the pressure of the pressurant tank all the way from 0 to the full pressure needed for the burn. So once the pressurant tank is filled, the next step is to fill the actual propellant tanks, which is what you see here under capacitor fill. And so going back to our diagram, this is the process where we connect the external tanks via these hoses and QDs at the bottom and fill the propellant tanks. And so note that because the connection to the external tank is down here, in addition to filling the tanks themselves, we're also filling the hard line all the way down here up until the QD, all the way down to the main valve. So this entire length of hard line for the LOX and this entire length of hard line for fuel is also being filled with propellant. And so as we're filling, or we fill all the way until liquid comes out of the vents on top, and that's how we know that the tanks are full, once we see liquid coming out of these vents at the very top of the tanks. And as we're doing that, we can monitor the level of liquid with our capacitor fill sensors, which stick out of the top of the tanks, but really just go through the tank all the way to the bottom. And so what these do is they output a capacitance that we can interpret as the fill level. And so those capacitance values are what we see in the chronograph under capacitor fill. So that's the fuel cap valve and LOX cap valve. And so one thing to note is that a higher capacitance, as is the case with fuel here, does not mean a higher level. Remember, we're filling both tanks all the way to the top, so they really both have the same volume. And so this different capacitance value is just a property of the different propellant. Different propellants have different properties, and that affects the dielectric constant, which is part of the formula for capacitance. So both these tanks are being filled to the top, even though it looks like one is going higher than the other. And so another thing to note is that if I zoom in here, once we've filled to the top of the tank, you'll notice that the capacitance value slowly begins to decrease for both tanks, right? It reaches its peak and then slowly is constantly decreasing. And that's because of boil off. So as the propellant, remember the propellants have very low boiling points, so they're constantly boiling while they're in the tanks. And so as it's boiling, the liquid is turning into vapor, and meaning the liquid level is dropping in the tank slowly. And that's this decrease that you see here. And so propellant boil off is also the reason for this pressure increase in the tank as we fill. You can see as we fill fuel, following this white line here, you can see that the pressure increases from basically 0 all the way to 40, slowly decreases, but then remains at a non-zero value. Same thing with LOX. As we fill the LOX, you can see the pressure spikes up to 120, and then stays at a pretty high value, relatively high, of 40 psi. And that's because propellant vapor is much less dense, so it increases the pressure of the vessel that's containing it. So that's why this pressure increases. And you'll notice that the LOX the pressure of the LOX tank is much higher than fuel when it boils off, and that's because LOX is a cryogenic, has a much lower boiling point, so it's boiling at a much faster rate, and just overall has more vapor in the tank. And so that's also the reason why we fill LOX second after the fuel, because it's boiling off at a much faster rate, and we're losing more liquid oxygen per minute or per second. We want to save as much LOX as possible, and that's why we fill LOX after the fuel, just to decrease the amount of time between filling the LOX and actually starting the flow. So after filling the propellants, all 3 tanks are filled, and the next step is to pressurize the propellant tanks to their operating pressures. So let's look at the diagram. So tank pressurization, or tank press, is the process where we open the pressurant ball valve and allow the high pressure gaseous nitrogen to flow through the propellant regulators and into both propellant tanks, pressurizing them up to the pressures that we previously set the dome port to. So at this point, the propellant main valves are still closed, so there's nothing flowing through the system, but the propellant tanks are being pressurized up to their operating pressures, which are the pressures that will eventually push them down through the system and out of the bottom. And so during this phase, we're looking especially at the propellant PTs, which is this right here for LOX, and this one for fuel. So this is going to see a drastic increase in pressure as this valve is open and high pressure gas is allowed to flow through the regulators and into this tank volume. And so let's see what that looks like. You can see if I zoom in right here, so this is after fill has occurred. We're looking at the LOX tank PT, which is the LOX PT I just pointed out in the diagram, and the fuel tank PT. So you see as we pressurize, the pressurant tank decreases from its high value, 3.5 thousand in this case, as the gas is being exposed to a larger volume, which includes both the propellant tanks. So this experiences a drastic decrease in pressure as the propellant tanks are being pressurized, and simultaneously you'll see that the tank PTs go from these low values all the way up to their operating pressures through the regulators. So LOX increases to around 600 psi here, and fuel increases simultaneously to around 620 psi. And so one thing you'll notice is that if you look at the dome pressures, the fuel dome PT was set to 640 and the LOX dome PT was set to 440. But these are not the same pressures that the tanks are pressurized to once high pressure gas is actually flowing through the regulators. LOX instead is around 600 and fuel 620. So not exactly what these dome pressures were. And so this is actually something that we have to characterize, so that the regulators are not perfect, right? Like the pressure that we pressurize those dome ports to doesn't exactly represent what pressure they're going to regulate down to. And so that's something that we spend a lot of time characterizing, like what pressure will the regulators regulate down to given a set dome pressure. And so in this case, we want these pressures in the tank, and we've characterized ahead of time what pressures we needed to set these regulators to. So once we've pressurized the propellant tanks, they sit at their operating pressures, and then we repressurize the pressurant tank to get back up to that 3.5 thousand psi that we need to sustain a full burn. Something else you'll notice is that this is the phase between tank pressurization and the flow itself, is the period of time that's most susceptible to overpressurization in the propellant tanks, because it's sitting there, the propellant is still boiling off, so it's still increasing the pressure, but it's already sitting at a very high pressure because of that pressure and gas. So here what you'll see is that boil off is, after pressurization, boil off continues to pressurize the tank, and then it gets dangerously high, around 650 psi. We don't want to go too much higher than that. And so what we'll do is we'll occasionally vent the tanks with the GEMS valve, just to decrease the pressure, relieve some of that gas, and then it continues to increase with boil off. And so remember, in the diagram, we do that with this GEMS valve. So this is a remote valve that we can actuate away from the system, and it's opening the tank to the atmosphere and allowing some of that pressure to be relieved. So once the tanks are pressurized and the pressure in tank has been filled back up completely, we're ready to begin the flow. And so the flow can be indicated with this blue spike on both of the graphs, which are the injector pressures. And so if I zoom in here, we can see this brief 20-second period that is the flow itself. And so another way to see the flow is with the thrust values, which, similar to the injector pressures, are basically zero throughout the entire procedures until we actually start the flow. So that's this period that you see here. And so you can see directly the flow data by clicking flow in the JIRA ticket. And so that takes us to the same frame of data approximately. And that's just the flow itself, which you see right here. And so real quick, looking at the diagram, the process of starting the flow simply involves opening the propellant main valves at the bottom, which creates a complete path for the propellants and the pressurant to flow to the bottom of the system, where the propellants mix at the injector, and we can ignite this mist to start the combustion, which creates the thrust that eventually will propel the rocket upward. So for 15 seconds, we're basically emptying these propellant tanks with the pressure of the nitrogen that is pushing down on the propellants, and they flow to the bottom of the system where they mix at the injector. And so that's why the injector PTs, which you see here, are zero throughout the whole procedures while these propellant main valves are closed. And then the moment we open them, you see a spike in pressure that is sustained throughout the burn. And that's because propellant is flowing through the main valves into the injector, and we can read those pressures with these PTs. So these two PTs, going back to the data, are these two blue lines right here, the LOX injector PT and the fuel injector PT. And you can see during the burn, it goes from 0 up to around 400 PSI. Same with the fuel injector. And then at the end of the burn, they decrease back to 0 when we close the main valves. So looking at the rest of the data, you can see that the pressurant, the moment we start the flow, is constantly decreasing as it's replacing the liquid in the propellant tanks, supplying more pressure to maintain these high pressures in the tank and the injector. So that decreases all the way down to almost 0. What else you'll see is the capacitive sensors, these fill level sensors, are decreasing as the liquid is flowing out of the system. So they start out almost full. Remember, some of it has boiled off at this point, so that it's not completely full. But when we open the main valves, the liquid starts to flow out of the tanks, and that's what this decrease in capacitance is showing. And so while there's combustion, there's thrust, assuming we have ignited the mixture. And so this thrust is the reading of the load cells. And so load cells are sensors that read a load or a force. And so during the combustion, you can see this increase in thrust that ends once we run out of one of the propellants. And then another thing you'll see is the engine TCs. TC stands for thermocouples. These are temperature sensors. So as the combustion occurs in the chamber, this is a very hot reaction, and so the heat is slowly being transferred to the chamber walls. And these temperature sensors that are along the outside of the combustion chamber will experience an increase in temperature as the combustion reaction kind of heats up the chamber walls. And so the end of the flow occurs once one of the propellants run out, right? Without one of the propellants, we can't have that full combustion reaction. And so in this case, looking closely at the capacitive sensors, you'll notice that the fuel is actually what runs out first, right? Because it levels off. You can see it decreases and then levels off before the LOX does, which means the tank has been completely emptied. And at this time, you'll see a spike in the injector pressure. And so this little spike occurs when the injector PT is exposed to gas instead of liquid. And so at this point, we close the main valves, and you can see all the pressures start to decrease. So the injector pressure decreases once there's no more fluid flowing through them. Same thing with the LOX injector, PT. And then thrust ends precisely at the moment where we run out of fuel, because without the fuel, there's nothing to burn and there's no more combustion reaction. Okay, so that was a pretty high-level overview of the flow or the burn itself. There's definitely a lot more detail that goes into the startup and ignition process at the very beginning, as well as the shutdown process. So like the various different aborts that can shut down the system and what exactly the shutdown looks like. And so if you want to learn a bit more about those specific processes, you can look at this Confluence page called Flow Walkthrough, Data Perspective. And so this kind of goes through the flow similar to what I just did, but with a bit more detail, especially near the end here with the startup, with the ignition process, and as well as shutdown with the various different aborts. So if you want to learn more about these things, definitely take a look at this page and read this text right here. But other than that, that's pretty much it for this video. I hope you learned something new. And as always, please remember to ask questions. That's the best way to learn. The best way to get over things that you don't understand is to ask any question. There's no such thing as a dumb question. So please ask any questions that you might have, anything that wasn't clear in this video or anything you want to learn more about. Ask any questions you have, whether it's on the Confluence pages, whether it's on Slack. Slack is probably where you'll get the fastest response, or in person, or even in this YouTube video comment section. Always remember to ask questions. That's the best way you're going to learn. So that being said, thank you for watching this video, and keep an eye out for more.